Ready to go? Okay. Hi everyone. How's been the conference so far? I guess this is a session between now and Beer and Gears. So we'll all enjoy that time. So I'll run through the session. Hopefully, not take a full hour and 15 minutes. Hopefully, we'll wrap around in half of that time, and then we will leave time for Q&A. So what we're talking about today is how to use load sharing to increase capacity in IP networks and in MPLS networks. A quick look at the agenda, why we need load sharing. We will look at some of the methods to boost capacity, and this is more of a review, how you can boost capacity in the networks. And then we'll dive into what are some of the methods, how you can efficiently utilize these increased capacity. And finally, the summary. So why do we need load sharing? There are like multiple reasons which come forth. Primarily, one of them is you need more bandwidth. If you have an existing infrastructure, you need more bandwidth, you can use load sharing to utilize your investment in your infrastructure. You may want to add bandwidth in small increments. For example, if you have 1 gig links and you need another 1 gig, it is more cost effective to take another 1 gig and bundle them together to get 2 gig bandwidth, as opposed to buying a new 10 gig link. You will use load sharing to increase protection in the network. So load sharing can offer you end-to-end protection in the network with diverse paths. It can offer a 1+n link protection. So you can have each link being backed up by another links. And the beauty about load sharing is all your paths, all your links, all your paths are always active. There's no idling of paths. Thus your investment is always being utilized. And then you always want to upgrade to the next bandwidth level. So let's say you're in a region, your transport carrier is offering 1 gig links, and you want to reach 10 gig links. And if you don't have a choice, the only option you have is take multiple of this 1 gig links, bundle them together to get 10 gig links. And finally, we know today 100 gig is not available yet, and it's going to take some time for that to happen. So load sharing is one way to effectively reach 100 gig. So we keep looking at that, we keep hearing from customers, they want to scale beyond 10 gig Ethernet, and now they don't want to wait the 2 years it's going to take for the standards to materialize and 100 gig to come. There's an ever-increasing demand for bandwidth in multiple networks, in service provider backbones, transit links, internet peering points, data centers. And all of these guys want 100 gig today. OC768 has been tried with some providers. It has turned out to be a very expensive option. Plus, furthermore, a lot of the current optical infrastructure being deployed today, that is optimized for 10 gig links. You take 10 gig lambdas, you transmit them across. There are very few which you can actually take OC768 and transport it across. So it doesn't come out to be a very effective option. So really, if you use equal cost multipath and combine that together with multiple 10 gig links, this is a far more affordable way of scaling capacity and of trying to reach 100 gig. What are some of the factors which affect load sharing? We all know protocols affect load sharing. You can determine multiple paths for ECMP through our protocols, OSPF, ISIS, and BGP. And these protocols essentially give you the path diversity, that you can create diverse paths in the network. Then there's link aggregation, which you can increase capacity between two nodes, between two routers in the network. And link aggregation is also called a link bundling, or sometimes also referred to as trunking. It essentially will give you the link diversity, that you have multiple links which will give you higher capacity. And once you set up all this, both the protocols and link aggregation, now how do you efficiently utilize this increased capacity? It depends upon the load balancing algorithms being used. How efficient are these? Is there ability to look in for the different traffic type? If you're sending layer 2 traffic, layer 3 traffic, is there some way those traffic can be treated differently for you to get the best utilization of the increased capacity? There are some more factors for MPLS, which are in addition to the factors on the previous slide. So for MPLS, there's LDP and RSVP-TE. They provide the LSP path diversity. So they can figure out multiple paths and over which the LSPs can ride. And then each router will make a decision over which path the LDP or RSVP LSP should go through. And there's also a matter on MPLS payload mapping. which is now in MPLS you're offering VPN services to your customer. Well, how do you map those services to LSPs? You can look at per service and per customer load balancing essentially, that a group of customers or one specific customer may get a specific LSP. Or how would all this traffic map to? So we will look at some of these. So let's look at how do you boost capacity in the network. So as we talked about the routing protocols, you can determine multiple equal cost paths to a destination. So your ISIs and OSPF protocols will affect paths taken by the IP traffic. Very common, they use the metrics and they use the SPF calculation. What is equally important is if you have MPLS network, these protocols also affect the paths taken by MPLS LSPs. So your LDP paths will actually follow the IGP topology. The best path in the IGP is what LDP will follow. RSVPT LSPs will follow IGP and IGPT topologies. So depending upon if you use CSPF or non-CSPF, it will follow IGP or IGPT topologies. And then we look at BGP. BGP can affect paths taken by IP traffic, whether they are within the AS through iBGP or external to the AS. And BGP also affects paths which are taken by the IP VPN traffic. You can have multiple equals cost BGP next hops, which could be reachable by diverse LSPs. You can also have multiple LSP paths to a BGP next hop. So what are some of the considerations and routing protocols you need to look at? Now this is on top of tuning metrics. You know, we're all familiar how to tune metrics. But other considerations are, what are the number of ECMP paths per prefix supported by a router? The more paths will give you a better path diversity. So this is something to look for. Support of ECMP with link aggregation. Very common these days that as you're going through a path, you will have link aggregation in there. A lot of your paths will have link aggregation. Well, all those are the link aggregation metrics correctly reflected for the routing protocols. So as an example, you have a link aggregation group, and let's say you're bundling 5 1 gig links together. If a couple of those links go down, do you still want the routing protocols to say that this is still my best path? Or do you want an option that they actually look at some other path which may now be better? So there should be options available where the changes in the link aggregate bandwidth are reflected in the interface metrics that the routing protocols can use. And finally, the router needs to support a very even distribution over any number of paths. And these are to, whether you have 2, 3, 4, 5, anything. I mean, there should be no limits of being bound by 2 raised to power n. It used to be the case that previously 2 raised to power n, like you will always, routers will do load sharing based on 2, 4, 8, 16 paths. So if you had, like, let's say 5 paths, internally they get multiplied, they get added to 8, and now you get an uneven load balancing. So this is the important criteria to notice for. In the case of MPLS signaling, so MPLS signaling allows multiple LSPs to the same destination. In case of RSVPTE, it will select a path for an LSP from the multiple LSP constraints. So let's say if multiple equal cost paths are present in the IGP traffic engineering topology, some of the criteria, some of the considerations which you can use is based on hops. You specify the LSP should take the least number of hops. The least number of hops means you're having less nodes, less number of links in network. This will have a less probability of failure. You can also pick a least fill method where pick the path with the highest available bandwidth. So as you're going your network, you distribute the LSPs fairly even across the network. So it gives you a better distribution of traffic. You can also pick a most fill case where you pick the path with the lowest available bandwidth. The idea is you pick each link at a time, fill the link up, then you go to the next link. This doesn't lead to an even spread of traffic, but it's more for the case that you want to leave room for higher bandwidth LSPs to appear. LDP also allows a prefix to be reachable through multiple equals cost LSP path. Typically in LDP, it's going to be a local decision by the router. The routing protocol will tell which are the best path, and LDP will just pick one of those paths. So now, once the routing protocols have established, the LSPs have been created, well, there's another factor. How is traffic mapped to this LSPs? If you take a look at the figure, we have router X has received advertisements from router Y and Z, and these are equal cost advertisements. So to reach network N, it has 2 equal cost paths. And it actually, to router Z, it also has 2 more LSPs. So between all these three LSPs, what are the criteria the router will use to pick the best one? Well, it can assign a prefix to a single LSP. And this will give a better predictability. You always know to this destination, all traffic goes over this LSP. It can limit that all prefixes which are reachable through that next hop within a BRF, I will assign to that LSP. So this way I can keep my customers or group of customers together. Then one group of customers get one set of LSP, one group of customers get the next set of LSPs. Or you can load share on a per flow basis. This is the most optimal. It will give you the best traffic distribution. However, again, it depends upon the policy of the network if you want to take that approach or you want to take one of the previous approaches. How does pseudo-wire traffic maps to LSP? So these are your VPWS and VPLS services. So in this case, the Ingress router has two equal cost LSPs to PE2. So what are the criteria it can use? Obviously, there is no IP routing involved in here. This is actually at layer 2. So the criteria it can use is it can bind a pseudo-wire to the least used LSP. This could be the LSP with the lowest number of pseudo-wires, for example. This will give you sort of like an okay distribution of traffic. You still run into the risk one pseudo-wire will overwhelm everybody else. You can bind the pseudo-wire to LSP with the most available bandwidth. This is useful for services where you need dedicated bandwidth. You're always looking at bandwidth requirements. You reserve bandwidth in the network. You'll say, okay, this LSP, this pseudo-wire is going to go over this LSP. I reserve this bandwidth. So it's not dynamic. It's more of a static in nature that you predetermine and reserve bandwidth. You can bind a pseudo-wire to an LSP. This is, again, the case if you want more control. You are limiting certain customers to certain LSPs. So maybe certain higher priority customers may get some higher priority LSPs, and nobody else can use that. Or finally, you can split the pseudo-wire traffic across the multiple LSPs. This will be based on flows. This will give you the most optimal distribution. So now let's come to the next level on link aggregation. So link aggregation, as you are already familiar with, is a very popular method of bundling multiple links together. It's used on both local side and network side. So you use it from the router and the provider to the customer, and also within a provider network, within data centers, within multiple places, essentially connecting multiple routers, multiple servers together. Now, typically, high layer protocols are unaware of the link bundling. What that means is, when your link bundling happens, it's a local decision between two routers. High load protocols are aware of that. And that does not increase the routing overhead as opposed to ECMP. So now, we talked about one option that does the link aggregation metric appears in the routing protocol. So that's an option, has to be determined on a case-by-case basis. If that link aggregation metric doesn't appear in the routing protocol, then all changes in the lag are pretty local. Anytime you add or remove links, there is no change in the routing topology. If you allow that to appear in the routing protocols, then yes, there will be changes in the topology. Some of the considerations for link aggregation is support for dynamic protocols like IEEE 802.3 LACP, previously used to call 802.3 AD. So this allows you to dynamically add and remove links, monitor the health of a link aggregation, and inform the other end that I am adding or I want to take this link out of service. So it really leads to an increased availability because both nodes are actively checking the health of the link aggregate. You would also need support for static link aggregation groups. So there's no need for any control protocols if you don't want to run. And also it works in multi-vendor scenario. If you are testing against servers, if you're testing against other switches, other routers, you don't know if everything will be interoperable. So static link aggregation is a good option. And finally, what is the lag capacity? What is the number of links in a lag? More the links, higher the bandwidth. If you can only aggregate 4 links, then you are limited by how much bandwidth you can get. If you can aggregate 20 links, that now opens up the field and you have more options to play with. And also number of lag groups. That once you don't not only want to have one lag, but you want to have as many lag groups as possible. So with link aggregation, we can also reach 100 gigs and today. So any lag, any router needs to support bundling of multiple 10 gig links to reach a bandwidth of 100 gigabits. So since 100 gig is still some time away, large number of links in a lag is the way to scale the network until 100 gig arrives. This is, as we discussed also, This is also compatible with the current optical infrastructure. If you're going over DWDM equipment, all the lambdas are tuned for 10 gig, so this will map just right in there. And if you are in a case that 100 gig is not enough for you, if you need to scale beyond 100 gig, let's say 200 gig, let's say 300 gig. So again, bundling of 10 gig links is one option that gives you. You can use some proprietary options, but this is really one of the most standards way of reaching beyond 100 gig to even 200 gig and 300. So this in QA was a summary of how different ways you can boost capacity. Now we will look at, now that we have increased the capacity through ECMP, we've increased the capacity through link aggregation, how can I tune that all my traffic going over these paths is effectively fairly well distributed among all these different equal cost paths. So firstly, there are two common schemes to load share traffic. One could be packet based and one is flow based. Packet based, again, most of you are probably familiar with this. Each packet is in turn sent on the next link. If you take a look at the figure, we have 4 packets coming into the router. The router will sequentially send packets on different links. So packet 1 goes on the first link, packet 2 goes on the next link, packet 3, and then packets in the first, packet 4 on the next. So this almost leads to a perfect load balancing. However, there is a huge potential for packet reordering issues. There's also a potential for increasing in latency and jitter for some flows because the router in effect is not looking at the flows at all. So a better way to do forwarding is using flow-based forwarding. So what's a flow? A flow is something which is based on the content of the packet. Let's say something like the IP header. So any 2 packets which have something common will be called a flow. In a flow-based forwarding, the prime function of the router is to keep the flows together. So if you look at this figure, the router considers packet 1 and packet 4 to be part of the same flow, and packet 2 and packet 3 to be part of another flow. So when it does the load sharing, it will keep the flow, all packets of flow A together. It will keep all packets of flow B's together. So what this does is it maintains your packet ordering. And packet ordering is very critical in a lot of applications. And within flow-based forwarding, hashing is one of the most popular ways for flow-based forwarding. Now we will take a look at, for flow-based forwarding, how you can take your different traffic type, whether it is MPLS, whether it is layer 2 traffic, layer 3, IPv4, v6, and send it across these different paths. So if you look at for layer 3 flows, for IPv4 and for IPv6, you can use source IP address and destination IP address. And this actually works in most scenarios. However, if you look at an end-to-end architecture, let's say between 2 hosts A and B, we will see all the traffic between the 2 hosts will always stay on the same links because the source IP and destination IP addresses are the same. So the hashing in this case is ignoring all the applications which are riding between 2 hosts. A better way to load balance is to look deeper inside the packet and look at the layer 4 information. So look at your TCP ports, look at your UDP ports. So once the router looks at that, and as we see in the application, the traffic between host and B is now utilizes different paths. So this will give you a better load balancing. And this is applicable for both IPv4 and IPv6. Some things to consider once you start looking at layer 4 is fragmentation. As we know, if an IP packet is fragmented, only the first fragment carries the layer 4 headers, namely the TCP and the UDP headers. This means the routers may consider the non-fragmented packets to be separate flows, and this may lead to packet reordering issues. So the solution which is recommended is in the application, set the TCP segment size lower than the IP MTU to avoid fragmentation. So that's one push you can do. At the same time, you can load balance fragmented packets using L3 information only, and then load balance non-fragmented packets using layer 3 and layer 4 information. So if your packets, if the TCP segment sizes are set correctly, you will end up load balancing based on layer 3 and layer 4. But in off case, some application not behaving, for those ones, you can still load balance using layer 3. So now, we will take a look at a test case. We will look at the load sharing in the IP network. So typical question being asked is, hey, we are using load sharing. What is the throughput when I use load sharing? Is it close to 100%? Is it 50%? Like how much traffic gets dropped if it's going over a link aggregate or an ECMP path? So in this topology, we put two routers together, connected to two test beds, which are the Ixia. So Ixia 1 has 32 1 gigi links, which are connected to router 1. And these will appear as 32 routed interfaces. Between router 1 and router 2 are 32 1 gigi ports, which are all bound together in one trunk. And then router 2 will output traffic to Ixia 2. The idea is all traffic coming from Ixia 1, when it hits router 1, it has to load share the traffic across that 32 port trunk row and to receive a router 2. And we will look at how the flows get, we'll look at what's the throughput which comes out. So we advertised 16,000 routes from Ixia 1, which got advertised to the router 1 and to Ixia 1. Ixia 1 transmitted 64 byte packets at 98% line rate. And this was a random distribution of about 127,000 source IP addresses, 127,000 destination IP addresses. The packets get load balanced across the 32 port lag. And then Ixia received the packet across 32 links. And we monitor the throughput on Ixia 2 to see how close it is to Ixia 1. So what we found out was this is the test results. The bar on the left, it shows the transmit stream from Ixia 1 port 1. This is the rate that it is sending. Other 31 streams are not shown for clarity purposes, but they were exactly the same. It's sending at a fixed rate. And what we found is the receive streams on Ixia 2 from port 1 to 32 are actually very close. It's almost virtually indistinguishable that how much packets or what is the throughput. So really there is virtually no packet loss. What we observed is between 0.1 to 0.2% is the packet loss. So if you're sending packets at 98% throughput, you can expect almost no packet loss. And what that means is that with load sharing, you can reach almost the full capacity of the bandwidth of the link aggregate. And now this is applicable for any random traffic distribution. One thing with hashing is you can come up with any test patterns where the traffic doesn't get hashed. So, but in a real life scenario, most traffic is going to be random. And so for a random traffic distribution, this is a good example. Now let's look at how traffic is load shared for layer 2 flows. So for layer 2 flows, they could be based on layer 2 information in the packet, the MAC addresses, the VLANs, the ether type. However, IP packets between two routers will always take the same path because the router, in this example, the router X and Y, they will have the same MAC addresses for all the packets. So IP packets don't get load distributed properly in layer 2 networks. So a better way is for any router or switch to look deeper inside the packet and determine if it's an IP packet. For IP packet, it should load balance based on layer 3 and layer 4 information. And for, of course, for the remaining packet, it will load balance based on layer 2. Now we take a look at MPLS. So MPLS has, essentially in an MPLS LSP, you will have three nodes, an ingress PE, a transit LSR, and egress PE. The ingress and egress behavior are going to be pretty similar to what we see already. So at ingress PE, which is actually the package which are entering an MPLS LSP, they could be coming IP packets from layer 3 VPN endpoints. They could be coming layer 2 packets from VPWS endpoints and from VPLS endpoints. So essentially, you apply the same principles that we looked at for layer 2 and layer 3 flows. So for IP VPN, you will, these are going to be IP packets, and you look into the layer 3 and layer 4 headers to load share those packets. For VPLS and VPWS, again, you determine at layer 2, but you look deeper in if it's an IP packet and load balance based on layer 3 and layer 4 information. So its ingress PE is essentially very similar to what we have already seen. On the egress PE, it has more fields to look at. So one option is it can load share based on per LSP and per VC label. So it has all the packets coming from the LSP on the egress PE have an LSP label, have a VC label. Now if it load balances based on that, The problem is you can have high usage pseudo wires or high usage VPNs which will overutilize one path. So again, the better way is to consider everything as a flow. Not only use your LSP label and BC label, combine them with the layer 2 and layer 3 load sharing that we looked at. So in the end, you get a better distribution, and you're able to consider flows based not just on the label but also on the packet content. Now we looked at, if you're looking at MPLS LSRs, so transit LSRs have no information on packet payload. They did not create the pseudo wire. They did not create the IP VPN. In fact, they have no knowledge what kind of traffic stuff is traversing over that. If they try to load balance just based on LSP label and BC label, it's the same problem. That high usage pseudo wires or VPNs will overutilize one link. And when I say transit LSR, it also includes PHP nodes. PHP are your penultimate hop popping nodes, where you pop the outermost label. But still, that device did not create the IP VPN, did not create the pseudo wires, it has no clue of the service. So a technique which is used to offset that is called packet speculation. With the packet speculation, the transit LSR speculates on the packet type. It looks at the first nibble after the bottommost label. If the first nibble is a 4 or a 6, it assumes this is an IPv4 or v6 packet. Once it assumes that, it can look into both layer 3 and layer 4 information to load balance that packets. Else, now you can speculate if your packet is Ethernet. In most networks today, the traffic over MPLS networks is going to be either pure IP or it's going to be Ethernet or a mixture of both. So you can say any non-IP packet is an Ethernet packet. You can speculate on that. And if you do that, now it becomes an Ethernet packet. You can use layer 2 information of the Ethernet, and you can still look deeper in the packet. And if it's within the Ethernet, it's an IP packet, as in the case for VPLS or VPWS, now you can load share based on layer 3 and layer 4 information also. Now we looked at how different traffic type is treated. Another thing to consider is the load balancing algorithm. And the utmost and primary job of any load balancing algorithm is to efficiently utilize increased capacity, meaning it must distribute traffic evenly. For example, if you have 32 port, 10 gig lag groups, the output of that should be as close to 320 gig as possible. That's the utmost responsible of a good algorithm. But there are some other considerations you need to look at. It's what are number of the fields in the packet header the algorithm can look at. The more the fields it can look at, the more options there are, the more it gives flexibility between layer 2 flows, layer 3 flows, MPLS flows, and the better the distribution. The number of hash buckets. What's a hash bucket? Is the output of a hashing algorithm. The bigger the hash buckets, the better the distribution. And then minimize correlation of ECMP with lag. Now it is very common that any router may be running the same algorithm for ECMP, same algorithm for lag. So if you're doing any forwarding, you may end up picking the same path for both. So any good algorithm needs to minimize the correlation between them. Or actually I would say even totally ignore any correlation. It should avoid any correlation between these two. And this will lead to a better utilization of the network. And finally, as we discussed, it has to treat each packet type differently. So both layer 2, layer 3 MPLS packet, the algorithm needs to treat differently. So let's take a look at another use case. This is the load sharing across a 32 port lag group. Similar test topology with one difference. From the tester, the XCR, to the router, there's only 1 gig link. So we say let's eliminate any effect from the tester to the router. Let's just concentrate what's happening between the router. So in this case, now 100,000 routes were advertised from XCR to the router, and the router advertised to the other router. And the XCR1 transmitted 64 byte packets at 1 gig rate. These were randomly distributed, 127,000 source IP addresses, 16 million destination IP addresses. This was total random distribution. And these packets got load balanced across the 32 port trunk, and then the XCR receives the packet. So what in this case we're doing is we are monitoring the traffic distribution on the link aggregate group. That how evenly is the traffic spread across this group. So here are the results for the traffic distribution. So what the chart is showing is the bars are, each bar represents the traffic transmitted on a port on router 1, and the bar represents, the rate represents the number of transmitted packets per port. As we can see, the transmitted packets are fairly linear. There's a minor difference, and actually I had to increase the graph. I originally started the graph from 0 to 6 million, and I could not see anything. So I made it from 4 million to 5.6, and I could see the differences now. And what that amounted to about 0.15% difference. That's the difference. That's the spread on the link aggregate group. So this is really a very small difference between packet rates across the links. And what that leads is the traffic gets very evenly distributed. So any good algorithm needs to make sure the traffic gets very evenly distributed across any ECMP path, across any link aggregate groups. Now, we looked at link aggregation, we looked at load balancing algorithms. There are some things you need to watch out. So this is an effect is called a polarization effect. If you have a multi-stage network, what will happen is similar routers will pick the same path for flows with an identical hash. Let's take a look at the figure. So packets which are going to network X, 2 packets, which are part of flow A and B. The first router assigns those 2 flows to the first link. What happens is every other router is running the same algorithm, so it will always assign them to the first link. So as we can see, all those flows will always stay together. What that means is your one part of the network gets overutilized, and that may not be good. So one way to avoid it, and that's something we call a basic hash diversification, is to introduce a unique ID in your hash calculation based on router ID, based on random number, anything. What that happens is, and again we go to the figure to see what happens. The first router assigns the package to the first link. The second router has a small offset. When the offset comes into play, it may not assign the package to the first link, it may now assign them to the next link. So that's good. So at least now you don't have one part of the network overutilized. However, what we see is the flows are still together. The flows have not been separated. So a better way to do is using an advanced hash diversification, where each router runs a variant of the hash algorithm. So it's running the same algorithm, but uses some variance in there. So again, I think the best example is going through the figure. We have 3 flows, A, B, and C, which are going to network X. The first router assigns them on the first link because they have the same hash. The next router is running a variant of the hashing algorithm. It will assign 1 flow to one link and 2 flows to the next link. The next router again separates this. So as we can see, this gives you not only a link diversity but also a flow diversity, so that all the flows now get separated across the network and you don't have the polarization effect. So in summary, load sharing is a very cost-effective technique to improve network utilization. It works over multiple paths, works over multiple links, works in IP networks, works in MPLS networks. There are multiple methods to boost capacity at various layers. You can tweak your routing protocols, you can tweak your MPLS protocols. You can decide how, in MPLS case, how IP VPN and layer 2 VPN traffic gets mapped to LSPs, how link aggregation is used, and all these techniques together will increase the capacity of the network. Once the capacity is increased, now you use flow-based forwarding to efficiently utilize this. You're using treating each of this traffic differently for layer 2, layer 3 for MPLS, using being careful about the load balancing algorithm being used, and especially watching out for polarization effects if they happen, and then take steps to neutralize them. And then finally, it's not a one-size-fits-all approach. You have to choose optimal schemes based on the traffic types and based on the policies in your network. Thank you. Questions?
Yeah, you mentioned that when you lose elements of a load shared link.
Yeah.
That you need feedback going to the routing process to inform it that there's less bandwidth there. And I'm sure you're aware many networks are designed so that you might have two link bundles that are designed to be backups for each other. Maybe they only are engineered to be utilized 50% of the time, or maybe it's an active passive thing. So there are some cases where even though you might lose one element out of 10, you want that entire link to appear down to the routing protocol to reroute all your traffic over the backup bundle of links. Are you aware of any work going on in that area and different router vendors, or who has implemented any features like that?
So, I mean, what we have seen is, and again, this is talking to some of our customers, is that they wanted not the whole link aggregate going down, but more like if one or multiple links went down, they wanted an option that this be reflected in the routing protocol. Now, this is not an option for everybody. A lot of people don't want their routing topology to keep changing, so they may not like that. So there's an option for them. I haven't seen anybody. I haven't seen, at least on our side, that we are hearing from our customers about if one link goes down, you actually bring the whole bundle down. So I mean that I'm not aware of. But I mean, in effect, if you do that, and if you reserve a full link aggregate just for a backup link, you're sort of not, you have this extra capacity which is not being utilized at all until something goes down.
Sure. So you mean, and a different approach maybe, instead of for the whole bundle to go down hard, maybe the approach should be instead to increase that path's metric to some really high number to say avoid this path unless there's just no other way out.
Actually, that's like what we have implemented. So it gives you, so you can increase, and you actually control how much it will increase.
Right.
So if one link goes down, you can increase it. If two links go down, it will increase more.
All right, thank you.
Hi, Chris Woodfield, Internet. If you want to go back a couple slides to the hash fate sharing issues.
This one?
Well, the one past that. Yeah, that.
Okay.
Yeah, there are a couple solutions. Actually, in our network, what we had to do to deal with the situation was actually use say source destination only at one level, and at the next level use source destination plus source destination port to solve a problem very similar to this. But one thing that we were, that I was surprised to find wasn't in any of the algorithms was any way to build any sort of per device random or semi-random seed into that hash algorithm. I mean, take the chassis serial number or something like that and use that to build some entropy into the system.
Yeah, I mean, so that's, I mean, you can use the per port, for example. That's something that we have implemented. So what we do is we give you an option, basically for a variation. It's almost random, or you can set that how much variation you want, and it will automatically variate the algorithm sufficiently that now your flows will be different. And this variation you can tune actually per line card or actually per system. So you have like different flexibilities there.
Okay, so you do have a solution for that issue then. Okay.
Any more questions? Right.
When you do a load sharing over multiple paths, how do you put into consideration of the link congestion, the latency of certain link? Number three is the quality of the link.
So and this actually goes back to the routing protocols. So load sharing is not independent. It is dependent upon the routing protocols. So for that means if a link is congested, typically it does not appear in the routing protocol that the link is congested. So if the routing protocol, unless you change the metrics, so unless you say that if my link is congested, I want the metric to go down. Now, if you're using MPLS traffic engineering, yes, it comes in there. Because in MPLS traffic engineering, you know exactly how much bandwidth on each of the links is available. These are reserved bandwidths, not dynamic bandwidth, but I went and reserved 1 gig out of a 10 gig link, so only 9 gigs left. Every other router knows that. So you can use MPLS traffic engineering for that. For IP, typically, the congestion is not reflected in there. So again, the way to design is with the load sharing, you also look at your link utilization. If certain so in a random scenario, in a random distribution, none of your links will be overutilized, except once you're approaching the limit, where then you will see most of your links will be getting overutilized. That means it's time to upgrade at that stage.
Pretty much on your last slide, you said you should watch out for polarization effects.
Yeah.
What do you look at to watch out for polarization
So-
effects?
It's, there are like two things. One thing is you can look at from the design perspective, If your network is very well designed, is very well structured, that, okay, I have all these aggregation layers. That tells you right away you will have polarization effect. If you have an arbitrary network, chances of that happening are very less. But in an aggregation network, you're taking feeds in. Let's say if you're in a data center, you're taking feeds in, aggregating, then to the next level, then to the next level. That tells you right away you will have that one. So that's one way of doing it, looking at the network design. Other is you got to actually hook up some testers there. So you look at dynamically that what is the utilization of the links, and if on each router few links are always utilized more, that tells you either you don't have enough random distribution, or you have random distribution, but you have the polarization effect in place. So again, you'll have to look through that dynamically.
Will a polarization effect cause hotspots to jump around, or will they always be on the same link?
Now, they should be on same links for the same traffic pattern. They will jump around if your traffic pattern changes. So maybe in the morning it's on one place. In the evening, if people are now coming in from home and logging in, it will be a different place.
That sounds like jumping around.
How do you manage the load when these equal cost links or lags are spread across multiple routers?
So let me repeat the question. You're saying is how do you manage the lags when they're spread across multiple routers?
Correct.
So you have one lag which is shared across multiple routers. Is it you're talking about?
ECMP share across multiple routers.
I mean, let's say if you look at ECMP, which is shared across multiple routers. I mean, really it's all based upon the routing topology. Now, when each router does a ECMP determination, it's based on the topology, but it is still an independent decision it is doing. There is nothing is informing the other router that, hey, I decided to go through you. So the way to manage is all routers should have, because every router will have control how many ECMP paths you want to have for different protocols. So typically, you want all the routers within the network to have the same number of ECMP paths enabled, whether 2, 4, 6, 8, whatever it is. If it is uneven, then it will not be managed, and then certain routers will get congested. Did that answer your question? Or? Any more questions? Okay, well, thanks very much for coming, and we hope to see you during the beer and gears.